Iggy Tan, Managing Director and CEO of Altech Chemicals. We've just announced a very exciting joint venture to build 100 megawatts of a new type of battery called sodium alumina solid-state batteries, and very exciting, game-changing technology for the grid storage market, Matthew.
Iggy, good to see you. Thanks for coming on and joining us. So sodium alumina solid-state batteries, what is that?
Well, as you know, lithium-ion batteries are the go-to batteries today. They're great batteries, Matthew, but there are some challenges with it. The first challenge is that you've seen on the news, they cause battery fires, explosions, and thermal runaways. So that's something of concern. Number two, they have a limited lifespan. So in an electric vehicle, you're talking about 8 to 10 years. And number three is that they operate in a very narrow temperature range. So you would know that lithium batteries operate around 15 degrees to 35 degrees, and they don't generally operate very well in the cold climates. So we've got a battery now that resolves that problem, the three problems. Our batteries are solid-state technology, and essentially it uses salt. What it does is that it doubles the life of the battery. So instead of 8 to 10 years, probably close to 15 years. It's totally fireproof and explosion-proof because the chemistry hasn't got the liquid electrolyte like lithium-ion batteries have. And thirdly, we have a wider temperature range. So we operate down to minus 15 degrees up to 60 degrees. And essentially, because we don't have that liquid electrolyte, it's all solid-state technology, we can operate in a very wide temperature range. And these are ideal in very cold climates and very hot environments.
Right. Okay. So we know that battery technologies and use cases will change and evolve because it's a relatively, one could argue, nascent industry as it pertains to electric vehicles. But this technology, with I think it's with Fraunhofer Institute in Germany, it's their technology, and they've JV'd with you. Why?
Yeah. So we didn't develop the technology. So you're right. If we develop the technology in our laboratories, you would expect the time frame for commercialization is going to be quite long. But essentially, the Battery Institute of Germany, called Fraunhofer IKTS, has spent 8 years in research and development, and they've already spent 35 million euros in this research and development. And in fact, they even have a 25 million euro pilot plan that are already producing these batteries that will destined for the grid storage market. And they were looking for a partner to commercialize that technology. They were looking for a partner that had land in Germany, that had a background in some battery technology, and also alumina experience, because the solid state part of the battery is alumina in the ceramic tube. So Altech fitted that criteria, and over the period we've signed a joint venture agreement where we own 75% of the joint venture agreement to develop 100 megawatt solid state alumina battery we call Serenergy batteries, to be built in Saxony, Germany. Very exciting news, and all destined for the grid storage market.
Right. Okay. So why have they selected you? Okay, you're going to do the commercialization component, but you're a relatively small company. Have they gone to other battery manufacturers before you and you've been pushed back, or are there comparable technologies out there which are being developed, alongside this, or like within the same time frame? Why you? I guess is the big question.
Yeah, and we've also asked that question. It's a good question. Why us? Why not a big German company? There are big German companies around. And their answer is essentially they're so big and they move so slow. They're not really entrepreneurial in their culture. And they tend to whereas we're much more entrepreneurial. We move faster. We can access the funding. And essentially, we're in a good position. We have land already in Saxony. We've already bought the land. and so it was really a great fit for us.
Right. Okay. So let's talk about the kind of commercial terms. We've talked about 75%, 25% in terms of the equity, but what are you committing in terms of capital, in terms of time, in terms of resources?
Yeah. So the next step is to conduct a bankable feasibility study for the 100 megawatts. 100 megawatts is essentially 10,000 of these battery units. So imagine a very big esky. We have about 40 of these cells in this battery, about 10 kilowatts. And the first project is to build a factory that will produce 10,000 of these modules for the grid storage market. So essentially, Matthew, grid storage is growing as fast as the EV industry. So it's growing from something like 4 billion to about 15 billion by 2035. And everyone is looking at grid storage because, yes, you have a lot of renewable power. Essentially, we want to capture that during the day where we're making that power and using it at night. So that's an important part of grid storage. Also, peak shaving or stabilization of the grid is very important. And so a lot of companies are looking at a battery that can actually do that job. And lithium-ion batteries do that. But what we're saying is our batteries, our Serenergy batteries, are double the lifespan, works in a very wide temperature range. And the most important thing, Matthew, is because we don't have any lithium in our batteries, it's just common table salt. And the issue with lithium prices, it's gone up sixfold in the last 12 months, and it's putting a lot of pressure on production costs of lithium-ion batteries. The other area is cobalt. 70% of cobalt comes from the Republic of Congo. And with labor issues and child labor issues, the industry are concerned about the ethical supply of cobalt for the industry. Also, graphite, 90% of graphite comes from China, and the industry is concerned about the geopolitical risks for one country supplying 90% of graphite for the lithium battery industry. And then finally, also copper. There's 2.5 times more copper in an electric vehicle than a conventional vehicle. And there's a recent report that shows that there's not enough copper mines being built or developed to even meet the electric vehicle forecast. So because we don't have those 4 elements in our battery, we just have salt and nickel metal powder, we are going to be a much cheaper battery source for the grid storage market.
Right. So I want to be clear about you kind of bounce around from grid storage or battery storage. And I think we've talked in the past about VRFBs as a kind of potential solution there. And you're also mentioning electric vehicles and the amount of contained metals in there. So the use cases for this are what?
Yeah, so whilst the batteries can go into the mobile business, we are very focused on grid storage because there is a niche there. Our batteries are very similar in energy capacity to the lithium iron phosphate batteries, the lithium batteries. So they produce generally takes 4 to 6 hours to charge and 4 to 6 hours to discharge, and ideally suited for the grid storage market. We think that the EV market is just too competitive. The grid storage market is growing as strong as the EV market, and we think that that is the niche that we want to concentrate in for an alternative to the lithium-ion battery.
I mean, Iggy, so I just want to be clear, with the mobile or EV sector, you say it's competitive, but could this solution be used in any kind of use case for that sector?
Oh, absolutely. I mean, it can be incorporated in trucks and buses and so on. But we're very focused on the grid storage market. So it's ideal for that market. As I mentioned, the life is double compared to your ion batteries. It can operate in a very cold climate. So, grid storage operates in very cold climates. So this is ideal for that. And totally fireproof and explosion proof. So you can put these batteries in a building, whereas in a lithium-ion battery, you can't have them in buildings because of the potential fire source.
Right. Okay. So, let's stick with the grid side of things then, because you're here to commercialize this. So, how do you go about doing that? Because if I look at the kind of the RFB space, it's very nascent, and there's lots of chat about it for the last few years, but no one's actually said, "Well, this is the definitive, design. This is the definitive route to market." There's no big players kind of really sort of stepping up and doing anything at scale. So how long to commercialize? How do you commercialize? And what's your take on moving this thing forward?
Yeah, so we're going to spend the next 12 months finalizing a bankable feasibility study for this 100 megawatts to work out what the capital cost is and the operating costs. But we are very confident that we are going to be 40 to 50% cheaper than lithium-ion batteries. In the whole process, we'll get offtake of the whole production for the 100 megawatts. And so that's the plan to commercialization.
Right, but it sounds like 4 hours to charge, 4 hours to discharge. It's kind of got it's like lithium-ion batteries. It's kind of got a short burst of energy rather than, again, VR. Sorry to hark on about VRP. I'm trying to work out where you kind of sit in this in terms of specific use cases versus, whatever use cases the VRP end up doing. So is it kind of, is that the immediate market is let's replace lithium-ion batteries? Yeah,
so we're saying that we won't replace the lithium-ion batteries. It is an alternate to the lithium-ion batteries, and because it's very similar to lithium-iron phosphate batteries, it's great at charging and discharging. If you're looking for high power very quickly, like in a sports car or a truck, you need cobalt and nickel in the lithium-ion batteries. These batteries for grid storage is perfect. You don't need that high power quickly. It is 4 to 6 hours to charge, 4 to 6 hours to discharge. So it works very well.
Right. Okay. So you're talking about, DFSs and so forth, and how you can, get progress things in country, in Germany. What about these kind of? You need customers, right? You need deals to be signed. The sight of money in the future to kind of get any kind of funding for these things. Typically, don't you?
Yeah, absolutely. So we're looking to get 3 off-takers for the 10,000 battery modules. There already have been a lot of these companies approach Fraunhofer IKTS already wanting some of the batteries, and obviously that's what they found us to commercialize it. So we think it's an exciting battery technology and really ideal for the time when you see all these pressures on prices of critical metals like lithium, cobalt, and copper, and so on.
No, that's very, very exciting. I mean, removing lithium, cobalt, graphite, and copper in terms of cost, fantastic. It's a game changer. Wonderful. But again, what's the process? I'm trying to understand the commercialization process. What is the actual process? You're looking for 3 offtake partners. One of them being your JV partner, I guess, for to tests and so forth, because you're building and constructing these things for them. But is it more a kind of you're producing a quantity where other people can sort of test this thing in real life situations, and then you look to sort of future longer term contracts? Is it really a proof of concept phase that you're going through now? And will you get financed off the back of that? Can you get financed off the back of that type of scenario?
As I mentioned, there is a pilot plant, a very large pilot plant. They're already producing these batteries, so we're well past the proof of concept stage. What we're doing is to design the plant for 100 megawatts. So you're producing something like 10,000 modules, and basically you're designing that plant as a manufacturing plant to produce these ceramic cells, put it into canisters, put it into battery units, battery management systems, and so on. As I mentioned, our technology is essentially a ceramic tube with salt granules in there with nickel metal powder, and this ceramic tube sits in a metal canister. That becomes the negative part of the battery. There's a positive terminal in the middle of the ceramic tube, and when you charge the battery, the sodium ions migrate across the ceramic tube to form molten sodium, which is the anode part of the battery. So it forms molten sodium, and when it discharges, the molten sodium discharges. So it's a self-forming anode in the battery, and it operates around 300 degrees internally. It's fully insulated, so on the outside of the module, it's actually, you can touch it, and because of that internal temperature, it's, I guess the analogy is a bit like a mammal. It can operate in very cold climates, and also it can operate in very hot, extreme conditions. So a very exciting technology that we're bringing to the market. Obviously, once we get the 100 megawatt plant up and running, our vision is to go into a gigafactory where we're producing many thousands of these modules.
I totally get it, and I'm gonna keep going on the commercial bit, because that's your job, right? That's what they signed up with you for, entrepreneurial and commercialization. So I get the benefits of, with regards to the temperature range has significantly increased from 15 to 35 to minus 15 to 60. Fantastic use case there. Fireproof in terms of, you don't get any of these runaways or these big fires that we see in the press quite often, and the reduction in terms of the cost, because the reduction in terms of the commodities which you need to, or metals that you need to put in here. But the demo, the pilot demo, full commercial production process is well understood in the space. So I'm trying to get a sense of what they have learned, and therefore what you now know about the pilot phase moving into demo, and how and what you want to do during that demo phase. Who's going to test it? Which markets are you aiming for? Which markets are wanting to interact with you as a potential solution? How long that phase is, and then how do you make money, right? When do you make money? Those sorts of questions. So I appreciate there's only so much you can tell us, but can you give us more on that front?
Yeah, so the 12 months of the bankable feasibility studies, as I said, designing the plan, really taking this, you're scaling up, Matthew. So they've already produced this in the pilot plan, but you're taking that equipment and you're scaling it up to 100 megawatts, and you're designing that factory. You're then designing the labor and all the materials that is required. You're sorting out suppliers for all that. The canisters, the alumina, all those things that needed to be sorted out. And then once we get to the bankable feasibility study, we will know what the capital cost is, and we will know what the operating cost is. And then we would go to the funding stage, and we would raise the money, either in grants, debt, or equity, to then build the factory. And the factory will take maybe 18 months to build. 18 months later, you're producing your first batteries, and you've already got your customers lined up. They will start taking the modules and putting it into grid storage applications.
Right. Okay. So,
and that's when you start making money.
For sure, I understand that. That's kind of like fairly generic process there. But what I'm wondering is, in terms of the economics, is what have you learned, or what has Fraunhofer been able to tell you? Because you're going straight into bankable feasibility study phase, right? So have there been any economic studies to this point to give you at least some sense of what this could look like, other than, hey, we've got a ton less metals in there, so it's bound to be really, really cheap. But how do you walk into this with your eyes open, as it were?
Yeah, so Fraunhofer have a very sophisticated simulation and financial models that has given us a lot of comfort of what we think the operating costs of these batteries are going to be, because we wouldn't be launching into this if we didn't have confidence that we are going to be making money at the end of this process. So, as I mentioned, the batteries are 40 to 50% cheaper than lithium-ion batteries, and that is really based on a lot of modeling and simulation that Fraunhofer has done over the 8 years. So we're relying on a lot of that information, and we're very confident that this is going to be a very competitive battery technology. Just from the fact that we don't have any lithium, we don't have any cobalt, we don't have any graphite, and we don't have any copper. From a layman's point of view, that just makes sense that it's going to be a cheaper battery. All we have is a ceramic tube, salt, and nickel metal in a canister.
No, I get the common sense approach to it, but I just wanted to test it because there's going to be a robustness behind this as well as the kind of more obvious stuff. Can I? So that sounds super exciting, and that's a process you're going to go through. How much money are you going to need to spend to kind of get through to the end of the BFS phase? How much are you factoring in? Have you got that money now? Will you need to go and raise that money?
Yeah, so we essentially have the money for the DFS phase. And obviously it's commercially confidential about that, but we are fully funded to get to the DFS stage. We've got 10.5 million at the moment in the bank, and we are expecting about 7 to 8 million coming in from a sale of a German subsidiary already that has been announced. So we are fully funded. We are working with the Fraunhofer people, so they developed a technology. We have a whole team of nearly 20 to 25 people that will be joining us as part of the feasibility study. We are not going to reinvent the wheel. They already know how to get to commercialization. We're essentially funding that process and giving them a free 25% free carry of the joint venture.
Okay, that's interesting. Okay, that's interesting. Well, look, super exciting project. Can't wait to see how this progresses as we move forward. What about the rest of the projects that we've talked about in the past? Are they going to now be parked up on the sideline?
Yeah, no. We still are focused on the Alumina anode project, which I talked to you last time about, coating silicon metal and coating graphite. So that project is still running. We are building the pilot plant on that project and doing the bankable feasibility study from that. So essentially, we got a leg in two camps. We got a leg in the lithium-ion battery camp, and we got a leg in the alternate, which is essentially a sodium batteries. So, and as you know, Matthew, sodium is a very reactive material. It actually sits under lithium under the periodic table, which shows how reactive it is. And sodium is freely available in common table salt.
Yeah, and there's a lot of it. There's a lot of it. So all kind of good news. So we're saying with the lithium-ion project, that is focused on the mobile EV. Yeah. With the Alumina solid state batteries, we're looking at grid storage. So slightly different markets, yeah? Okay. Yeah, absolutely. Makes sense. So we should be looking at both projects in parallel. We shouldn't be, you don't necessarily prefer one child over the other in this case then?
Exactly. Yeah.
And no cannibalization of markets. Even better.
Yeah.
Iggy, super exciting news. Like I said, I'm really keen to see how this progresses and want to see what the take up is and see who may come to your side and who may be interested in this as we move forward. So I appreciate your time today, Iggy. Thank you.
Thank you for having me, Matthew.